Wait, where's my papers? Okay, today we are going to do integrals. 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 Before we do this, we should probably go back to the beginning of time. So first there was this thing known as the Big Bang. And it was just like a giant explosion, just lots of color, lots of bang. Just a big explosion, a big bang, just started the universe. Then came a guy known as Isaac Newton. Isaac Newton. I'm going to spell that out here because I'm just going to assume that nobody can spell Isaac Newton. ISACNEWTON. Alright, Isaac Newton. Let me just draw his face right here as a circle. It's got like some squiggly lines. Has some hair. Isaac Newton. Let me just make the hair orange. Let me just variety. Change up the colors a bit. A variety of colors. Some orange hair right there. Alright, so Isaac Newton basically invented calculus, and soon after came the concept of the integral. That's the integral. Okay, what I encourage you to do now is pause this video and go take a hike. Think about your life. Take some Adderall, because I am not going to stop talking, and I will never change my pitch. Alright, let's look at a parabola. Let's look at the graph of a parabola. Let's get started with a new color. Let's go with a blue. Alright, so we've got this parabola. Let me write this. Alright, parabola. P-A-R-A. I apologize, guys. I'm not that good of a speller. O-L-A. A parabola. Let me just draw that right there. There we go. Parabola. Maybe blue isn't the right color. Let's switch to a purple for that. Yeah, purple. That works out. Draw purple right there. Okay, so we've got this parabola. And I know you guys know what an x-axis is, but I'll just repeat it more times than necessary while overemphasizing it with a new color because I like colors. X-axis, 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 x-axis. The integral is similar to sigma, and that the integral finds the sum of a set of values. But whereas sigma finds the sum of values over discrete intervals, the integral finds the sum of values over a continuous set of values. For this reason, the integral is good in determining the area under a curve. For it finds the total sum of values under a certain set of points for every point the entire way through. The integral can be thought of as the antiderivative. Now, if we were to draw a secant line across this parabola, we were to draw a secant line right there. Let's switch some colors. Oh. I apologize, guys, for that. I forgot to take my Adderall. Anyways, the secant line across a certain portion of the curve can be viewed as approximately equivalent. The slope of the secant line can be viewed as approximately equivalent to the slope of the line tangent to a certain point along that curve, because if you were to take the change in x value of this secant line and reduce it to 0, you have the limit definition of the derivative, which is the slope of the line tangent to the curve. As well, the area underneath the secant line, let me draw that in with some red. The slope underneath the secant line can be viewed as approximately the area underneath the curve. And because the slope of the secant line, or what's approximately the derivative, is the equivalent, is approximately the change in y over the change in x, and the area underneath the secant line is approximately the area underneath the curve, or the change in x times the change in y, it can be shown that the integral is essentially the antiderivative. Because of this, shortcuts to calculating the integral can be found in inverting the shortcuts to calculating the derivative. Let's say you have a function c times x to the n, where c is a constant and n is a value exponent of x. Now, when writing an integral, you write out this S shape at the front and include a dx at the end to show that it's in the change of x. The integral of this would be equal to c over n plus 1 x to the n plus 1 plus a value c. For if you were to find the derivative of this new function, let me just emphasize that in a blue. The derivative of this would be equal to this value over here.
What I want to teach you is about related rates. Related rates are literally just how f of x is explicitly related to f prime of x, and vice versa. Related rates can trace their origins to the dinosaurs. I'm going to change to green. When the extremely smart Triceratops would calculate the rate of decrease in volume of a watering hole. The Triceratops' brains were extremely smart for their time, being the size of a pea, thus becoming the smartest being of the Mesozoic era. The Apatosaurus and the Stegosaurus come in a close second place, with brains the size of a grain of salt. Triceratops, Apatosaurus, and Stegosaurus were all ornithischians, which were bird-hipped, but the saurischians, lizard-hipped dinosaurs, were the ones that actually evolved into birds. Whoops, I got off on an f prime of x. Today we're going over related rates. So, related rates. These are applications of various elementary formulas with a twist on derivatives. This is used to find a change in area, volume, an angle, and given a certain rate, you too can find the changes in volume of exciting things like balloons, melting candles, change to a yellow for a nice fire, falling ladders, and the most exciting of all, conical cups. First, one must find the formula of what is to be found, such as the area or the volume, etc., etc. Then, plug in available constants which are given and find the derivative. So, if this side is like 2, and this base here is changing at a rate of 2 meters per 2 meters per second. So plug in the rates given prior and solve for what the question asks. Ta-da! You've just done a related rate.
So what I want to do in this video is find the derivative of both sides of the equation. I will find the derivative of both sides of the equation. On both sides of the equation, I will find the derivative. So instead of finding the square root of the derivative of the tangent line, you can solve equations such as those for circles. Let's switch colors here. Circles, C-I-R-C-L-E-S, like that. In this manner. So to better understand implicit differentiation, you... Oh, sorry, I have to take a call. Hey, what's up, girl? We still meeting at Starbucks later? Yes! Oh my god, he did not! Girlfriend! Okay, I'll catch you later, okay? Bye! Alright, so let's switch to the color red. So when we use implicit differentiation, we need to apply what we know about the chain rule. Implicit differentiation is just an application of the chain rule. We're just using the chain rule while finding the derivative of both sides of the equation. So let's write this out again. So this function here is not y explicitly stated in terms of x. So we must find the derivative of both sides and use implicit differentiation. So the derivative of x squared is, of course, 2x. The derivative of y squared in terms of x using the chain rule is 2y times dy dx. And of course, the derivative of a constant is 0. So all we have to do at this point is solve for dy dx. Let me just change colors here. Let's say blue. So we're just going to solve for dy dx, and that will give us negative x over y. That looks just about right.
Perfect. Close enough.
Uh, so, that is the fundamental. Alright, so next, we're going to do differential equations. Let's switch colors here to an orange. I think orange sounds good. So differential equations are a method with which one can determine the change of one set with the change of another. It is related to implicit differentiation and the integral. So in order to do differential equations, you first take the dy dx equation and isolate the sides. So let me give you a fundamental example of what a differential equation will end up looking like. So dy dx, let me fix that, plus a c constant. So I will write c y to be blank will always end up equaling, or almost always end up equaling, cx to the blank plus c. So this c and this c are arbitrary constants which will be given with the integration, but this c is an unknown constant because you cannot find the the exact formula of y based on the integral. So, for example, here I have a function dy dx equals x over y. I'm going to do Christmas colors. dy, I want to draw dx in red, so I'll save that. And so here we have a function dy dx equals x over y. So in order to be able to fully solve this, I'll be able to give constants. So x, when x equals 2, and when y equals 4. Ugh. Guys, if you have handwriting like this, I hope you don't take my route and live in your mother's basement. Unfortunately, the only writing as bad as mine is my doctor's. So, if you want to spend 10 years in the medical field, feel free to do so. Okay, anyway, I don't want to start out too hard, because I want to give you an example you won't just skip over. First, one must multiply both sides by y. So, hold on, let me move that over. No, cut it. Oh, well, whatever. Multiply both sides by y. Actually, I want to do this in another color. Purple. Where's Christmas? Multiply both sides by y. So now, those y's cancel. And now you have y times dy dx equals x. So now, we must multiply both sides by dx. Apologize for my handwriting. So the dx's cancel out, and y dy equals x dx. Now, just take the integral of both sides, and you get 1/2 y squared equals 1/2 x squared plus that C we were talking about. Alright, I run out of room, so I'm gonna scroll over. Okay, okay. So, with that in mind, we know that x equals 2 and y equals 4. So we can plug in a 4 for y and a 2 for x. So that will be 1/2 times 16, since 4 squared is 16, which equals 1/2 times 2 squared, which is 4, plus c. And if you multiply the fractions out, you get 8 equals 2 plus c. And subtract 2 from both sides, and c equals 6. That's not the answer though. What we are looking for is what the function is. So now we know 1/2 y squared equals 1/2 x squared plus 6. So you multiply both sides by 2, which will end up with y squared equals x squared plus 12. And then take the square root of both sides, so as to isolate y, and thus y equals the square root of x squared plus 12. This is the answer. Thank you for watching this informative video on various topics of calculus.